Hello and welcome to the Side One YouTube channel. My name is Ray, and in this video, part 14 of the SpotMicro build, I'm going to continue looking at the program. So in the last video I actually added these brackets in, and the two prior to that I talked about the kinematics. So one of the things I needed to do is be able to control the speeds of the servos, where they go, trying to approximate a straight line, or at least get servos to finish all at the same time with their movements, so I don't get unusual jerky movements. So to that end, I've been creating the leg speed control routine. Now, again, we're going to be using maths from time to time, and I've created a few helper methods, which I haven't really used in the end, and I'll get to that later. One of the ones I did make that's useful is this set all servo speeds. So this allows me to set the speeds of all of the servos at the same time to either a set speed or to turn off speed control altogether. Speed control's handy in as much as we can set all of the speeds. One of the things some of the routines that I'll show you do is actually slow the speed control down to 0 on some servos that have no intention of moving. It's a side effect of the way the program works. Okay, so let's move on and we'll have a look at the first one. So what I've done is I've used the naming convention. S is a speed control, move is obviously I'm moving something, and foot is an individual foot. So this routine allows us to move an individual foot to a specific location. Now this one is a relative movement. That is, it works out where the foot is currently and then moves it relative to that. Now, one of the things I have done is turn the servo power off because it's got issues. Okay, that rebooted everything. Alright, so one of the things that we've got going on here is we wanted to be able to select an individual leg, say the front right leg, and move it forward or back or left or right or up or down based on, or from its current position. So I can just specify an amount to move it. This can be handy if you're trying to balance your robot, for example. So using the inertial measurement unit, which is located on the top of the robot, we could calculate out where the robot is and what we need to adjust to make it level. So that's what this routine is all about. It will actually, first off, we check and make sure all the speed settings that we're using are sane. So our speed setting here is sort of like a percentage where 1 is 100%. We've set 1% or 0.01 as our minimum speed, and everything else that we can have anything in between those ranges. We're using the same numbering convention as I used in Forward and Inverse Kinematics. So leg 0 is our front left, leg 1 front right, leg 2 back left, and leg 3 back right. And the first thing we do is we work out where is everything at the moment. So we need to know where our servo positionings are at the moment. At the moment, this program is not actually running. I can launch the program and get everything set up so it's all resting, and I'll do that shortly. But at the moment, there's no power on the servo, so I can move them freely. So once we work out where all of our things are, so all of our joints, so that's the shoulder, the wrist, and the shoulder, the wrist, the arm and the wrist, We also record or make a note of, this is mostly to make the equation easier, what the maximum speed setting is. So if you go right back to the config routines, we actually set the various velocities. So in this case, this one here, they are back right shoulder velocity is actually set back in the servo config. And I can actually go back to servo config, back right shoulder, and we've got back right shoulder velocity. So that's where we set our speed, way back there. And we did the same for all of our servos. Each one has its own unique speed in case we use different servos in each of the different joints. Once we have all that information, we calculate out a position. Now this is actually a library of information position returned from the Forward Kinematics, and that gives us an XYZ coordinate of where the foot is relative to the center of the robot. When we do that, we then pass that into the inverse to get our servo pos while adding in. So we've got our positions X, Y and Z. We get the X, we add into it the requested amount to move it, along with the Y, the amount we want to move it, and the Z, the amount that we want it to move. And that comes back with a set of positions that all the servos have to be in that leg for that to occur, and that's returned in the dictionary servos. Part of that dictionary is also an error value. If you remember back to part 12, when we calculate out where we want to put it, there is always the possibility of trying to put a foot outside of the allowable range. So when that occurs, we return an error. So we have a look at this first before we attempt to move any servos, and we check to make sure that there is no errors. Assuming there are no errors, after we do our check, we've got to do some more math. So what we're going to do is we're going to work out how much of a change there is from where the shoulder joint currently is versus where we want it to be. And because it can be a negative or positive value, it could be moving in or out, we're going to use the ABS function, which returns just a positive value. We get the current, get where we want to go, subtract the current position, that'll return a positive and negative value, which we put through an ABS to return a value. We do that for the arm and the wrist, and then we do a little bit of maths. So we divide the shoulder offset by the velocity, which is going to give us a time in seconds of how long it's going to take it to actually move the servos at full speed to those positions. So we get our 3 times. We then do a little bit of an if, else if set of commands where we check to work out which has the longest runtime. So if it takes longest to get the shoulder there relative to the arm, and shoulder there longer relative to the wrist, we're going to use this set of equations here. Whoops. And we're going to set the speed by the velocity times the speed that we have requested. So sometimes we don't want this to run at full speed. We don't want it to run a little bit slower. If the back end of this robot suddenly drops to a sitting position, it will have enough rotational inertia left to flip it all the way over onto its back. I know that because I've done it. So we control its speed as well. So using the shoulder velocity multiplied by speed, we get the shoulder speed. That's assuming it's moving we're going to take longest to get there. We then apply arm divided by the shoulder time, or the wrist divided by the shoulder time, to get the other 2 speeds multiplied by their relative speeds using the velocities that we've assigned as the maximum velocities. If arm time is the highest value, then we use the arm time, otherwise we use the wrist time, and we then calculate out what speeds we need those servos to run at so that all the servos will complete their movements at the same time. Having worked all that out, we check to make sure the servos aren't moving first. That's actually a routine up earlier. It's just comparing where it's going to versus where it's told to go to. And assuming it's not blocking, assuming all of our servos are stationary, it will then check to see which leg we're playing with. It will then set the speeds and then tell to move those shoulders into those locations. Assuming, of course, that the speed is greater than 0.1. That's 0.1 degrees per second, which would be very, very slow. Alright, so this one's pretty straightforward. We do the same thing for each leg. And then we've got S-move foot 2. Unlike the previous one, which is a relative movement, this is an absolute movement. That is, we're telling it where in 3D space we are moving this foot to. So we're giving it an X, Y, Z coordinate relative to the center of the robot. Before we can calculate out our move so that all the servos finish at the same time, we need to know where all the servos are at the moment. We're also going, because we're going to apply the same formula to for each of the legs, and we're only working with one leg, we're going to grab the current velocity for the selected arm, and then we're going to work out the servo positions of where we want to go. So we're going to actually calculate out what position each of these servos would be at for our destination. In this case, minus X pot, or this is for the front left leg, which is going to be on the far side. But if you remember correctly, the inverse kinematics only really works on this side. So we're going to take the negative value of what we've passed in and subtract off that LXS, which is the length between the X axis and the shoulder, like the center line of the X. We also do the same. In this case it's forward, so we're going to YPOS plus LYS and ZPOS, which has no offset. And we're going to pass that into the leg inverse kinematics routine. That'll return a dictionary of servo pos. We do that for whatever selected leg we've passed in. You can see some commented out print statements. That was me debugging the routine to find out why it wouldn't work before correcting things. I did find I had a few errors at times, which have all been corrected. I can probably remove those print statements completely now. So assuming we had no errors in where we want to go, so it is possible to produce an error by asking it to put a foot where it can't reach. We now are able to work out a shoulder offset, an arm offset and wrist offset. That's the distance it needs to travel on each of those different servos to achieve the target. And we can do the same as we did last time for shoulder time, arm time, wrist time to calculate which one takes the longest. And then we calculate out what speeds we need for all the servos to arrive at the same time. Again, we check to make sure that none of the servos are moving first, and then we apply the speed and then send the command to actually move the servos. And that results in the foot arriving at the position with all the servos stopping at the same time. Now, this has been for one leg only at a time, and it does work to a point quite well. There are a couple of caveats with this. These will rotate at a constant rate in order to achieve their target location, and On a pivot, it's always going to be an arc, so these do not move in a straight line. And depending on where you're moving from to, you can actually find the foot will move in an arc. So that's something that we will look at in probably in the next video. So this is just speed control at this stage. I have got S move feet, where we move all 4 feet at the same time. This has been very handy to implement some gestures, and so I'll get into the gestures shortly. Gestures allow us to combine multiple movements together or in a sequence to complete a movement. So I can actually make this robot crouch, sit, lay down, and get back up again. I can even do it without him falling over, which is a major bonus, and you may have seen short clips of videos of that working. Basically, we're doing the same as what we did for the individual feet, but we're doing this for all feet at the same time. And so, as you can see, there's a lot more parameters being passed in, and we're also passing in the speed. First thing we do is we work, in this case, S move feet. This one is the relative movement. In other words, it's moving. We pass in the number of millimeters to move the feet. A positive number is going to move it forward, a negative back, a positive number up, negative down, or we've got a negative going to the left and a positive going to the right. So we need to calculate out where is the foot now. Once we know where the foot is now, we can then work out what the positions of the servos have to be to get it to where we want it to go, and that could be as simple as moving it forward 60 mil. We might want to move all the feet forward 60 mil. We then calculate out the offset. So we do this for each servo, how far we want to move the servo in this movement, and we do that for all of them. In this case, we're using that ABS again of the where we want to put it, subtract where it currently is. We can then calculate the time it's going to take to complete that movement, and that movement might be 0, in which case the time is going to be 0. We then work out, in this case we're going to use a common variable called big time. This is the biggest time that was used. We'll set it as a front left shoulder, but if the front left arm is bigger than big time, which we previously set, then we'll set it to be the front left arm. Then we'll repeat the same test for each of the different joints, and if the biggest time that we have will end up in big time. We can then use that to calculate out the speed at which the shoulders or the joints will move. We can set their velocity or set the speed, and we will check them first, make sure nothing's moving. Then we'll apply the new speeds, and then we can apply the new positions. And so this will move all of the feet at the same time at those speeds. So that's all pretty straightforward. We've also got S move feet 2. This is the same as the move, except we're using an explicit destination so we can tell it the XY coordinate for each of the 4 feet. So what I think I might do now is start up the program code, and let's have a look at some of those in use. Okay, so now that we've got that back up and running, I've got the clock on the LCD running as well. This is a very simple routine I put together just to display the time and prove that the LCD is working. Eventually we can have that display other information, but for now it's showing the time and showing that it works. So let's have a look at some of our example scripts. So one of the first things I want to do is we've got rest 0.3. How about I actually type on the right window? Rest 0.3 is a very simple command to simply tell all the servos to move back to the rest position. So let's say I move the arm up, we'll move the arm back a bit. If we go back to our Python, we run that script, it'll bring it back. Now, the rest command drives the servos directly. It doesn't go through any of our other linear routines. I can specify sit 0.3 is the speed, so I'll go slow. We'll sleep for 2 seconds. And then let's crouch. Leave another 2 seconds and then rest. So we can execute that series of commands. So if you let's go through that again. So that's where we're at this point in time with that particular set of programs. I need to get linear movement working properly first before we start the walking sequence. So I'm going to try something risky, and with it on the table, I normally do this on the floor so that if it rolls over backwards, it doesn't have far to fall. Try that again. We'll slow our rest command down a bit, I think. So execute. Looking at that, our back legs are a little bit too far forward of the pivot point when it gets weight on the robot. Doesn't look too bad, but it's enough that when it straightens that up, it throws the whole robot back. I think there is a command called up. Let's try that one. That's better. Just move that robot forward a little bit more. So we have got getting up, and this is what I was talking about with if we don't do this in the right sequence, it will fall over. So at some stage I will add in the finite state so that we'll only move from one position to another following a set of rules. Well, that'll do for this video. So if you like these videos, don't forget to click on like, subscribe, ring that notification bell so you're notified when future videos come out. It's also a form of support that costs you absolutely nothing, but does help the channel a great deal. If you'd like to help the channel further, you can join my VIP Patreons Go Lucky and Lorenz Berger, or my Builder Patreon MRL45, in helping to produce these videos. All my Patreons do get these videos early. I also have a Discord channel where notes on the development of the program and how it's working. I do post up notes. I answer questions as well on any of these builds, so if you've got questions, by all means come into the Discord. And we'll see you in the next video.